undersea environment, like the outer space environment, offers many problems as well as many advantages to mankind. A major problem is the design and construction of facilities in which man and his machines can work efficiently, protected from the hostile elements that surround them. Project DIVERCON 1 was proposed by the Naval Civil Engineering Laboratory as a means of finding some of the answers. Assisted in the early phase by a class in engineering design at UCLA, laboratory engineers conducted a series of highly successful experiments. The object of DIVERCON 1 was to investigate the problems of underwater construction, the work to be done by divers. The UCLA students developed a 52-inch model consisting of 2 metal rings which could be joined together to form a vertical cylinder with a closed top and an open bottom. The model incorporated 3 major design features: a rod and V-block method of aligning the separate rings, a quick connect latching system with special tools, and the gasket material used to seal the joints. The model was tested in an open tank on the UCLA campus. Divers performed the assembly operation in the tank, effectively demonstrating the use of the alignment devices, the clamps, and the special tools. When the model was fully assembled, an air hose was used to force the water out of the interior and test the seals. Then, as a final check of the assembly features and equipment, the model was taken apart and removed from the tank. The UCLA contribution had proven of great value. Now, the same model, along with another that was connected by bolts rather than clamps, was tested by NCEL personnel in 50 feet of water off Anacapa Island. Since the assembly problems were well under control, the emphasis in these tests was shifted to the handling of the materials, and particularly to the lifting device. The test models had been placed on the ocean floor intact. The plan was to separate the parts and reassemble them again, starting with the clamped model. The disassembly procedure posed no problems. A pneumatic winch was used to reassemble the components. The winch line, after it had been passed through the lower ring, was attached to the upper ring. And the upper ring was drawn down into place. In the ocean environment, the mating guides, latching system, tools, and sealing gaskets again proved to be effective and easily handled. Even under the sea, a construction job attracts its quota of sidewalk superintendents. The lifting device was the only piece of gear that was less than satisfactory. It was constructed of 2 34-inch diameter buoys mounted in an angle iron frame, with the buoys interconnected and open to the sea at the bottom. Control was accomplished by adding or releasing air, carried in scuba bottles attached to the device itself. The lifter was free-floating except for a safety line fastened to the concrete slab base or anchor. The divers operated this skyhook device by remote control. They experienced some difficulty in maintaining the proper degree of buoyancy required to lift and move the separate parts of the facility. It was particularly hard to achieve and hold a state of neutral buoyancy without overcompensating. The bolted test model was put through similar tests, and it was immediately apparent that the quick latching clamps were greatly superior for fastening the modules together quickly and easily. This was the only significant point of difference. With the model test phase completed, the divers headed for the surface for the last time. In January of 1968, the full-scale DIVERCON 1 dry repair and storage facility was ready for testing. DIVERCON 1 was visualized as a structure that would model the problems of large-scale ocean floor construction and still be of a size that could be handled by a small number of divers. The structure itself was 10 feet in diameter and 10 feet high, comprised of 3 prefabricated modules: a bottom ring, a middle ring, and a dome top. Again, the tests were conducted at the site off Anacapa Island in about 50 feet of water. The assembly techniques were well established by now. As before, moving and setting up the lower ring were first in the order of procedure. There were significant differences, however, in the DIVERCON structure and in the lifting system. This time, the structure was designed to stand on adjustable legs, which could be set to conform to the sea bottom and thus maintain a level. The method of lifting and moving the components had been greatly improved. The lift, or skyhook device, was now an open-end cylinder that traveled back and forth on a line. The line was anchored at both ends, forming a sort of trolley cable. It provided a considerably more positive control of the lifting operation. The actual raising and lowering of the modules was done by a hydraulic winch mounted in the lifting device. The winch received its power from a control console located on the sea bottom, which contained a hydraulic pump run by an electric motor. Electric power for the motor was supplied by the surface support vessel. The hydraulic control for the winch and the pneumatic control for the lifting device were also located on the console. The middle ring was raised and placed in position, and the two sections were fitted together. The latching system functioned as efficiently as it had done in the previous tests. Normally, the divers are able to communicate by means of signals. In this rather involved operation, however, they were supplied with special underwater writing materials for exchanging more detailed information. In this case, the written messages referred to the final phase of the assembly, placement of the dome on the structure. The first step was to run the winch line through the vent hole in the top of the dome and down to the anchor under the completed sections. Then the dome was winched down into place and mated to the assembly. To prevent an unplanned separation, the lower compartment of the lifting device was flooded, and the latches were secured. The load was unshackled from the lift device, and the winch line was removed. Then the structure was tied down to the 30-ton anchor block to prevent it from floating away when it was filled with air. The tie-down lines ran from the base of the dome through restrainer blocks on the lower ring, and then to the anchor. The requirement for maximum safety dictated the use of this deadweight type of anchor. This completed the main structure of DIVERCON 1, and the task had been accomplished with relative ease and few serious unexpected problems. One important additional feature was included in this test. NCEL engineers had constructed an underwater lighting chandelier designed to provide overall illumination for projects of this kind. As part of the experiment, the divers demonstrated a method of handling and placing it. The chamber was constructed of lengths of pipe. To move the chandelier conveniently, it was necessary to achieve a state of neutral buoyancy by blowing some of the water out of this chamber. This was done by using the pneumatic hose under the watchful eye of the underwater photographer. When the desired state of buoyancy was reached, the divers had little difficulty in maneuvering the chandelier into position, which satisfied the objective of this brief test. DIVERCON 1 remained on the bottom for about a month until a recovery ship became available. In this whale's eye view, the task of recovery was getting underway. Marine growth had covered the structure during the intervening weeks. A hook was lowered from the ship and attached. When the hook was properly secured, DIVERCON 1 was hoisted to the surface. The test was complete. It resulted in some minor modifications being made, but no major revisions of the experiment were considered necessary.